Yeah, good morning, everybody. Let's wait for one or two more minutes before we start the webinar so that others can also join us. So please give us a bit time. There's still people still coming. Okay, so maybe we can start. So good morning again. Welcome to our webinar. My name is András Kis. I'm from REKK, Regional Center for Energy Policy Research. And I will be coordinating this meeting. I would like to make two technical announcements. First is the meeting is recorded and it will be later available as a video through REKK website. So if you have other interested colleagues who would like to check it out, then we will post it and you will be able to share it with them. And the other announcement is that as you have seen in the agenda, we are starting with the presentations, but then we will have a Q&A session, questions and answers. And then later on, we'll have a second Q&A session. The first one is targeting technical and engineering questions. The second one is about energy markets and economics. And you should be having on your screen a little chat box. So you are able to post comments and questions even during the presentations. You may also post questions during the Q&A sessions. But during the session, the Q&A, you will also have a chance to speak up to contribute orally. So that's the plan. The other technical feature I wanted to announce. And with this, let me hand the microphone over and hand the floor to Daniela Cegar, who is head of energy management from the Novi Sad Water Utility company, who is in the company of Mr. Nikita Ivic, which is the technical director of the water utility. So Daniela, please, the floor is yours.
Thank you. Good morning, ladies and gentlemen, participants of today's webinar. My name is Daniela Cegar, the head of energy management of the public utility company Waterworks and Sewerage Novi Sad, and in my presence is the technical director of our company, Mr. Nikita Ivic. On behalf of the management of our company, we would like to welcome you to this event. Public utility company Waterworks and Sewerage Novi Sad, founded in 1949, provides healthy drinking water to over 135,000 households in city Novi Sad and suburban settlements. The system distributes around 1,500 liters per second to consumers from water plant Strand, which has advanced technology that improves the quality of drinking water. The company has a task to supply consumers with about 105 million liters of water every day, with increased water consumption in the summer and requires high electricity consumption. If we add to that the energy to move wastewater through the sewage network, it's about 1,200 kilometers. Our company is consuming significant amount of electricity. In attempt to find solutions to reduce that consumption and costs, the company decided in the spring last year to join the partners from Hungary, DHI and REKK in project energy saving in the water sector. Despite the ever-present pandemic situation, we hope that the people involved in the project were able to analyze the water system and find solutions for improvements in terms of energy savings. We hope that the results of this project will be interesting and useful to participants of the webinar. Let me thank you for your time and attention today, and we invite you to take an active part in webinar. Enjoy the work.
Thank you very much, Daniela. And now let me invite Gábor Benedek from the Western Balkan Green Center to introduce his organization briefly to the audience. Gábor, please.
Thank you very much. I have a short presentation which I will try to share with you. Please confirm if you can see it.
Yes, we can.
Okay, fine. So thank you very much for the opportunity to be here, and we are glad to see that this exact project is getting closer to its finish, and the results are about to appear. I believe it would be good for the participants to hear a few words about the Western Balkans Green Center, which is a green development agency of the Hungarian government. The Green Center was founded in 2019 based on concept prepared by the Global Green Growth Institute, and the Ministry of Innovation and Technology of Hungary is the sole owner and the oversight institution of the Green Center. Our aim is to do our activities for the benefit of the Western Balkans region, to contribute to the country's climate protection efforts and green transition. This is done by project preparation and technical assistance programs in line with the nationally determined contributions set forth in the Paris Agreement on Climate. The Western Balkans Green Center has 3 business lines. The first one is the investment preparation, which is done through grant programs. One of them is the WBGC program, and the REKK is the beneficiary of the first program of ours. The second business line is the preparation and setting up of a green investment fund based on the projects prepared by the grant programs. And the third business line is the operation of a Center of Excellence in Green Transition for the Western Balkans. This one is an in-house project of the Green Center, and I believe it has great opportunity and great promising opportunities for the future, just like the other 2. So I will tell you about a few words about it. The WBGC grant program is operating since 2020. It finances project preparation, capacity building, and pilot projects in the region. Our target countries are the 6 economies of the Western Balkans, and eligible activities has a wide portfolio. I would say that any activity, be it preparing a feasibility study or a market study or a capacity building type project, can be financed in the grant call, provided that it has relevant and well-grounded climate adaptation or mitigation effects. Right now, we are about to roll out our third call for applications. It has been published a week ago and open until 6th of August. Its system and its details are much similar or very much similar to the first and second calls. So Hungarian-based companies and academic institutions and civil society organizations are allowed for grant, and we very much encourage international consortia formed with organizations from the region, because we believe that their presence in the project and their knowledge on the ground is inevitable for a relevant and successful project. Because of budgetary restrictions, we cannot finance directly foreign companies. Therefore, we prefer consortia if it's possible. The Green Investment Fund is currently under preparation. Right now, there are 25 projects in our portfolio. One of them is the one which we are talking about right now. And the Green Investment Fund should be able to finance investments prepared in the grant program by incorporating public and private resources and mobilizing and catalyzing private resources. It should begin its operations in the next 1-2 years. Right now, it's the concept and its establishment is being prepared. And our third business line, the Center of Excellence in Green Transition, is, as I said, is an in-house project of the Western Balkans Green Center. We realized that the region has great challenges in terms of preparing their legislative and regulatory framework to be in line with the EU regulations and requirements. Therefore, capacity building type projects are of great need. And this unit or institution of the Green Center should be able to focus these type of projects and reply to the local needs. We are preparing this Center of Excellence in cooperation with the energy community, and the Memorandum of Understanding setting out cooperation details and founding the project was signed 2 weeks ago by State Secretary Attila Steiner of the Ministry of Innovation and Technology and by Janez Kopač, Director of the Energy Community. So the Center of Excellence in Green Transition is operating right now. It will run capacity building and technical assistance projects with a base in Budapest and an outreach to the region. In the end, it should accelerate green transition by sharing Hungarian and European knowledge and expertise with the region, and of course, learning from their knowledge and how to do. Capacity building projects should be or could be study visits, cooperation platforms, workshops and conferences, but on the midterm, we are preparing twinning programs and longer term webinars and conferences too. We believe that the Western Balkans Green Center's activities and also this Center of Excellence has close connection to the Green Agenda for the Western Balkans of the European Commission. And although our financial resources are not comparable to this one, but we could add to the success and to the goals of the green agenda. And Commissioner Arvaji also agreed with this one when he joined our program 2 weeks ago. So we are eager and we are glad to continue our operations, and we are open for any need, for any talk from the region and from Hungary. So I would say that I'm glad and we are glad to see the project of REKK being finalized, and we hope that its result will add to the development of the region, to the development of Novi Sad. And as the third call for applications is currently open, I would encourage anyone and everyone to apply for funding, because the more promising projects we have, the better results we will reach. So thank you very much, and I wish you a successful workshop for today.
Thank you very much, Gábor, for your presentation. I think it has been very informative, and it's great that the Hungarian government is making efforts to establish new connections to the Western Balkan countries, and at the same time contribute to climate mitigation. So thank you. We'll go on. Now we start to discuss details of the project that we have been doing. I believe that Zlatko's screen appeared, but Zlatko, before you start, I prepared 2-3 slides about the project in general. So if you don't mind, let me share my screen. If you can undo your screen sharing. Okay. Okay. And now you should see my PowerPoint. I just wanted to make a review of what we have been doing, just to give you the framework, and then we will discuss the professional details in the upcoming presentations. So some key figures. As Gábor Benedek has been discussing, the Western Balkans Green Center is providing assistance for such projects, and we received a substantial co-financing from them, which made it possible to establish this partnership. And we have 3 partners. The beneficiary utility company is the Novi Sad Water and Wastewater company. Then we have REKK, which is the Regional Center for Energy Policy Research. We are specialists in energy, climate, and water economics and policy. And last but not least, we have DHI Hungary. We'll hear more about them. This is an engineering firm which has been doing the hydraulic modeling for the Novi Sad water system, which was an essential, very important component of our project. We started this work about a year ago, and we are about to finish it now. So this webinar, in fact, it's a dissemination webinar. We already have results that are worth sharing, in our opinion. For those of you who are not familiar with drinking water and wastewater companies, this is a really very, very sketchy chart here. We have drinking water abstraction and treatment. Then this water is pumped into the network to reach the customers. The wastewater, the sewage, is collected through another network, which is the sewer. And finally, there is the wastewater treatment plant, which is taking care of the sewage before releasing it back to water bodies in a clean form. All of these components can be substantial energy users. And in the case of Novi Sad, based on the project concept, we focused on the drinking water network. And in fact, within the network, we selected one area, which is the SREM area. Novi Sad is kind of like Budapest, for those of you who know. There's a flat part and there is a hilly part, and the SREM area is the hilly part. And even though only less than half of the consumption of drinking water takes place here in this area. The drinking water networks electricity consumption, the majority of it takes place here in this area. So this is the place that offered the largest possible energy saving opportunity for us. So we wanted to know about this opportunity, whether there are sensible measures that can reduce energy use. And this was part of the engineering analysis to create a hydraulic model, and Zsuzsa from DHI and Erzsi from DHI will talk more about that. And based upon this calibrated model, to start testing different measures, different scenarios. And as you will learn, pumping efficiency has been the way forward, identified by our experts, our engineers. Then within REKK, energy market forecasts were created to know the value of the saved energy. If you're talking about an investment into energy efficiency, we should know what are the returns. And these forecasts, since we are talking about long-term investments, these are very important because we want to know not only the current price of electricity, but also the price in 5 years, 10 years, 20 years. We also quantified the related or the background CO2 emissions, because the electricity is purchased from the network, and there are some power plants which are fossil fuel based, and they emit carbon dioxide. So we wanted to know what is the carbon dioxide emission related to the energy consumption and also to the energy savings of the Novi Sad Water Utility company. And finally, once the energy saving measures were identified, we wanted to estimate the cost of these measures, the cost of the investments. And then when we have all of these components together, then we can create a cost benefit analysis to see how feasible these measures. This is a key output of our project. At the same time, during this 1 year, we also wanted to provide or share some of our knowledge and some of our experience with the employees of the Novi Sad Water company, especially about the hydraulic models operation, which they can continue to use after the project ends. And then we have dissemination as also a key target. We are holding this webinar today. There will be a report in English in the coming months, and the executive summary of this report will be translated and made available in the Western Balkan languages. So in a nutshell, this is the project concept, and within today's session, we are going to start. Zlatko will tell about the Novi Sad Water Utility company and the drinking water network. Then DHI colleagues will talk about the hydraulic part, and then we'll go on to the economic components of the project. So I hope that you will find it useful. With this, I'm ending my presentation, and let me hand the floor to Zlatko now.
Hello, everybody. Do you hear me?
Yes.
Okay. So, ladies and gentlemen, now we are going in now deeper technical aspect of this project. I will make some kind of introduction of the project to describe you water network, water system of city of Novi Sad. That is second largest city in Serbia, with a population about 400,000 people. Now I would like to share my presentation with you. Is it visible? Do you see it?
Yes, we can. Yep.
Okay. So the official name of the project is Energy Saving and Greenhouse Gas Mitigation Potential of the Drinking Water Network of the City of Novi Sad. I am a senior engineer in development department in company Waterworks and Sewage Novi Sad. So I was some kind part of the team in our company in this partnership with Hungarian designers that are involved in this project. So, water system of Novi Sad generally covers, just a second, covers whole area of city of Novi Sad and suburb settlements that are connected to this one water network. As was mentioned already, capacity of our system is about 1,500 liters per second. About 1,200 kilometers of pipelines and mains consist of, and about 55,000 services. This basic data are quite updated, so we could, using a lot of data in this project, in this cooperation, through the modeling of a network, part of the network, but hardest part of the network, water network of our system was possible, and we finally got something that was a calibrated water network model. Non-revenue water, average non-revenue water in last year was about 30%. Through the Novi Sad pass Danube River. So the left bank of water system is flat area with approximately 11 meters above sea elevation, and it is quite simple part of the system covered by one main pump station and two more another secondary pumps that just increase pressure, minimum pressure. On the right side of the bank of the Danube is a hilly area, so-called Srem area of the system. That is consists of a couple of settlements. That is very complicated, with a lot of pressure zones, consumer zones, reservoirs, pump stations, typical for the hilly area water networks. In the past, water company of Novi Sad succeed to establish a mathematic model of a water network of this left bank of a flat area calibrated model. but honestly, it was easier way. But everybody who ever tried to establish a model knows how hard it is in general, especially for big systems. So this right bank of the Danube was a subject of our project, in a sense, to establish a model, to calibrate it, and finally to make energy efficiency analysis with some case study and cost benefit design with the propose that designers finally gave to us as a final report. So this is a SREM area network, water network system. As you see, there are many pressure zones colored in different colors. Consist of settlement Petrovaradin, Sremski Karlovci, Bukovac, Sremska Kamenica, Popovica, and Ledinci. Each of these settlements is also established as a district meter area. So each of them have flow meter and pressure meter in front of the in an input point of the area of the DMA. So this part, the subject of the modeling was a network, approximately 200 kilometers of pipelines with 15,000 connections, mainly house connections, with the individual houses, connections, services, 15 reservoirs, 14 pump stations, and finally 15 pressure zones, with a population of about 60,000 customers. I made the questioning sign here because the census, the last census, you know, the counting of the population was established last time in 2011, and we expect it to happen again next year. And that's a tricky question in this moment for us, because the city of Novi Sad has increase of population, very big increase. So in this moment, nobody can precisely manage the number of customers in this year, in this moment. And it is one of most important thing when mathematic model established, when consumption has to be calculated and to get results that should be similar as possible to real consumption and flows. Srem water net area has, in that sense, was an extreme complex system for modeling. This dozen of pressure zones are splitted, physically splitted with a breaking of pipeline of closed valves. And it was important during this designing of the model to define each point to be very precise and detailed in this process to really establish the model as similar as possible with the real position in the system. Also, the database of consumers should be established in a manner that each connection was at the place, at the node, at the junction of the system in the model as it really is in the field. In this part of our network system, average water losses are higher than average, so they are bigger than 30%. That was also very important thing for modeling, because as you know, water losses, it is necessary to be included in a balance of consumption. And it is very important to achieve a realistic data of it, not just to get an average amount. Also, as usual, in these hilly areas, pressures are average greater than usual. So on the left bank, on the flat area of the system that consists about 70% of our network, average pressure is about 2.5 or 3 bars. In this right bank, SREM area that was subject of the modeling, average pressure are greater, about 4 or 5 bars. Fortunately, our company has a GIS databases, GIS department that was established about 15 years ago. So until up to date, we have a great database of our network and sewage system. Of course, it's permanent work. It updates every day. So we were aware of errors and mistakes that still exist in our GIS system, and through this modeling, we had to make corrections of this database. As I mentioned, each of this settlement in this SREM area is established with the DMAs, so it was possible to go on with the modeling of SREM area network on the level of calibration to be calibrated. And we pick a period period of modeling that was 2019, September 2018 to September 2019. It's a period when we covered and analyzed data in model. So it was also possible to, beside consumption, use data from SCADA system, online method measurements that was archived in our servers that we used through this advanced period of calibration of model. Also, pressure was used in this process. On this picture, this is Popovica settlement, a typical settlement of this Srem area. Very small settlement with maybe 2,000 of consumers, but very complicated in the same time in hydraulic way, with a couple of reservoirs and pump station for each pressure zone. So that's a typical typical settlement that was analyzed in this area, in this model, and that's the reason why we up to date we didn't succeed to have a model of our network in this part of water system of Novi Sad. But finally, unfortunately, through this cooperation in this partnership with the designers from the DHI and REKK, they did it, and finally, so here we are in this final presentation at the end of the project with the successfully established model that was actually a base for the further step of this project. That's an energy efficiency analysis with the results that will be explained to you during this webinar in the next presentations. So I just explain it and describe this system. Hope that you can now have insight just to understand how does this system works, how it looks like, to make an introduction for that, and to can follow easier next presentation where my colleagues from Hungary will go deeper in technical aspects of this project. So this is just one sketch of our GIS platform that we use every day, and the database used in this modeling was actually got from this huge amount of database from our GIS database. So thank you very much. I hope it was useful, and now I think Zsuzsanna has to go on with the detailed description.
Thank you, Zlatko. I think this has been a great introduction to Zsuzsa's presentation, and I don't take any more time. So Zsuzsa, please.
I hope that you can see now. Can you see it?
Yes, but it's not projected yet.
Okay. It's okay now, right? Okay. So I hope that right now it's fine. So welcome everybody. It is our pleasure to be able to present you the results of the project from our part where we were responsible for. It was a very challenging and an extremely nice collaboration, I have to say. It was challenging because of the pandemic, and also that we could not meet personally, just only at the beginning, at the end. But the collaboration was really great, and let me thank here all the inputs, all the effort, and the great job which was done in the Serbian side, the water utility company. Without them, this project and this result, what we have presenting right now, wouldn't have been possible to carry on that level. Indeed, this, as Zlatko presented, our task was to define the network system, to describe the network itself from the water supply perspective, how the energy is used. So it means that we were using our expertise as a team, and where we had different people involved and contributed to the work. Indeed, the overall aspect of this project was that to find a way how the energy consumption could be linked to the energy market forecast, which was a quite interesting topic, and actually to explore what is as the potential for water utilities, because we believed, and that was the project idea itself, that the water utilities are among the very big consumers of the energy. And if you take it into consideration what kind of energy saving potentials we do have, it's not necessarily only the pumps which do take up the energy itself. So that's indeed that we took the system from the very broad perspective, having to the focus on the system itself, indeed also with the individual elements included. So at the end of the project, we have developed the suggestions for the changes in terms of better operation as well. Indeed, we also contributed for the cost-benefit analysis of these suggestions, how to move on. And also what was also quite interesting from our perspective is basically to give the outputs in terms of carbon footprint, indeed the CO2 saving potentials to have the contribution in the global climate change combating aspects. So it means that how we are able to quantify these improvements was one of our targets, which is definitely one of the steps that's considered to be done if we're speaking about the mitigation in terms of climate change. So in this, if we are having a look on the system itself, as Zlatko also mentioned, that the system key performance is always the question. So there are always key performance indicators in where we do need to describe the system performance, which is indeed always interesting if you're having a look on the water quantity, quality, also from the hydraulics, for example. But indeed, when we are also having a look on the system itself, only from the energy consumption perspective, so there are groups of people who are dealing with only with the energy, but not necessarily with the hydraulics together. They do have also the vision that let's save as much energy as it is possible. So indeed, when it comes together, the hydraulics, water quality, and energy, then we are arriving to really, I would say, the complex systems. And in that, as Zlatko mentioned, the pressure management and the non-revenue water is always the key targets also of the water utilities in terms of the water savings as the kind of environmental indicator in the operational performance indicators as well. So indeed, the big challenge is right now that if you would like to put together all these things, how it is possible, how to set the operation if we would like to fulfill the energy use optimization, we would like to fulfill the system hydraulics expectations and the water quality issues, especially in terms of very complex systems, and what we can gain if we start to understand the system, and what we can gain if we're really having a look into the backside and reviewing all the potentials, or at least selected many potentials. So that's there comes here the questions that what we can do if we take this line. So where we can arrive, if we do the business as usual. So each of the water utility has its own mindset, how they operate the system, from the habit and from the, I would say, business as usual, because this is what they know, this is how they feel that it's the grounded base, because they have many years of experiences. Indeed, we were also interested what will happen if we change our habit a bit, only a little bit, which means that change in a bit of operational rules, and we try to, in some terms, risk something which is out of the business as usual. Indeed, that's the question also comes, what will happen if we even invest into big changes, whether there are options for do kind of big changes, but potentially driving to the big gainings. And then again, as the unusual approach, if there is any gain, if we look at savings from the non-standard perspective. So it means that indeed we can analyze this kind of what if we do the scenario analysis of them. And in this, we know more about the system behavior, then we can, of course, we can better plan what we can do and how we are going to do, because we know how to make it. So it means that actually, and then also as Zlatko mentioned, this is a very, very complicated system, but to describe the system behavior and to deliver it into the kind of understandable way, we need the digital twin, we need the description, the visualized descriptive method of the system, which is could be delivered in the way of calibrated hydraulic model. So indeed, that it was very interesting when we had the discussions and when we had the workshops and all the work that we have done, that as usually, and it's in general, and the water utilities, as from our perspective, there are, I would say, separated groups working in energy, in hydraulics, and GIS department. But once we are putting these teams together as the pre-requirement to do the hydraulic model, then it comes to the common knowledge, the common experience, which can gain and which can drive us to a very, very high level of system performance analysis, system performance understanding, and of course that can come and can lead to the, I would say, very good results in terms of delivering of the good potentials for system improvement in terms of measures, by the means of investment, and also by the means of operational changes, or maybe all together. So indeed, this was the way how we moved on in this project, and indeed that was the method that we applied. And big thank again for the team and for the excellent collaboration that we had with the water utility company members contributed to this project. So it's these kind of experiences and data and measurements and the very advanced systems what water utility company had already as the good ground for this work were used in our work to come out with the suggestions how to put these things. As Zlatko mentioned, that they have the 15 years established GIS department, which was very, very important for this work. And indeed, it was very, very important that they had really the geocoded information. So it was very well handled. It is still very well handled and improving, I would say, daily, which is really, I would say, the good base for our work. So this is something which I believe that the water company can, I would say, be proud, and which gives the good potentials also for the other type of the works what they are doing. Indeed, at the end of this project, we were able to make the calibrated model, which we are, let's say, presenting right now, with some of the hints from this, because there is no that much to go into very much details, and we will about to give you some of the I would say outlooks, some of the results, what was achieved. And indeed, we used also our unique approach, which was developed within this project, and the unique tool to answer it, and the challenge that how to link energy and hydraulics, and how to link the cost-benefit analysis and the economical market forecast. So it was the big challenge also for our water expert team. To develop this link and to have the work of the complete different, I would say, other sector, I would say the energy sector experts in that one. So indeed, there's a solution what has done, and indeed we really forward, we indeed, we really implemented the work in such a way that we described the entire system, not just only bits and pieces of the system, and we had a look what happens. Because as we mentioned, and also as we had, that once we see how we modify something as one element in the system, that means that also we could see how this modification of the one element is moving on in the system. So as you see that the system is very, very complicated, and my colleague, she is going to explain you a little bit more in the following few slides, that if you made a change in one part of the element, as it contains 14 pump stations, but 14 pump stations meant here 55 or approximately something like that, if you have a better pump itself, so pump units. So if you change something, that is definitely changes the hydraulic conditions and water quality in the system. So it was very much important to provide such a system which describes this from this perspective. And this could be also presented towards different units in the water utility company, which is targeting only one area or one unit as the target, as the field of expertise. So who is responsible for one pumping stations could see the impact in another pumping stations as well. Because, you know, as you are working like I would say in the airports, in the tower, there are so many flights going there, and you cannot concentrate for a very long time for all these patterns. Here we have the descriptive tool, which could be, I would say, substitute this, and you can concentrate on your task, but with this help, you are able to see what's happening in the system itself. So we made the calibrated system, which described the current state operation itself. We made the scenario analysis based on this as the operational and then energy consumption aspects. So we made several scenarios, and based on this, there was the cost analysis, which contributed to see the different scenarios from the energy consumption perspective. We were able to deliver the results in terms of tables, graphs, and all the kind of necessary inputs what the energy experts could use later on for the cost-benefit analysis and also for the market analysis. So it means that we could arrive on the level that we understood all the impacts of each of the scenarios that was developed to understand what does it mean in system hydraulics, basically, and also in terms of the energy use. So, and in terms of energy use, which means energy cost, and which means the potential calculation of the CO2 footprint. So then let me give the floor to my colleague, to Mrs. Erzsébet Piesko, who was the leader of the modeling team, who is now describing the modeling which has been done, and also pick up one or two results which was delivered and discussed.
So just really shortly, that our main aim was to develop such a model, as already Zsuzsanna and Zlatko told you, that model can describe all of the operations inside the network, and it includes as minimal as possible schematization inside its operation. So that was our main aim, that to have this operational model, that this extended time period model to develop based on longer time period statistics that can be used for further analysis. So altogether, what you can see, this is what you can compare it with Zlatko's presentation before. Some small schematization were needed, but altogether we have all of the main hydraulic elements of the model implemented. So all of the 45, we ended up adding one more, so it's outdated. Yesterday, the presentation. So some of the reserve pumps are also implemented, and all of the tanks and braking chambers were implemented to the model. so that it's not just serving that purpose for the cost analysis, but also serve as the operational tool in the future for the water utility. So, and also as many of times we mentioned, the system was rather complicated. So all available operational rules were implemented, or control rules were implemented for the current state model, and also some were developed for the future use of the model as well, for the different scenarios for the as part of the energy optimization part. As mentioned, the model is calibrated. Altogether, we used 46 locations for calibration plots. It's included measurements of the network of flow, tank levels, and also pressure plots to use. And we use it as to calibrate the model itself. So we have the hydraulic model based on the GIS, customer information system, and other sources available, made with commitment with the group together with the local users and the local water utility, some changes in the model and some cleaning and revision of the already available high quality model, high quality data. But it needed some, so to say, some improvement to be implemented inside the model itself. So this digitalization and revision of all of the information in one platform was integrated in our model, and also it was integrated the local knowledge of the experienced users and experienced operators, because some of the data cannot be written inside, so to say, PDFs or Excel sheets or GIS system. Some of the local water utility members really gave all to be able to build a very high level of model for this network. So in the end, we calibrated for a selective time period in 2019 September. But we also used validation data from other time periods. So as Zlatko mentioned, we used 1 year time series to be able to have this model. And in the end, we also have not just this workshop as mentioned. We also have the transfer of knowledge to the local water utilities, and also partially to REKK as well. They partially also needed to learn some parts of how to use the hydraulic models, because all of our discussions were based on these findings of the hydraulic models, and later on it's planned that they are using on their own for their own analyses. So actually the photo on the right is one of the workshops. This is one we have only they were able to hold in person. The others were held in online. So altogether, we developed different kind of scenarios. It's mainly based on energy use review of the hydraulic network itself, and also it is partially based on the results of the hydraulic energy. So to say, the energy audit was based on already available measurements data, and also based on the hydraulic model. The energy optimization consists of the review of the pumps operation, their efficiency, and also a system-wide energy audit. And based on that, we not just we came up different kind of scenarios. Some of the scenarios you can see it on the slide itself, but and also what later on András and Enikő will present in the later sessions. We also took account not just the technical and operational aspects of the network, but we also took account what would be more, so to say, what would be more beneficial in financial aspects of energy usage. So that's why it is hard to say how many scenarios we actually had. We actually started over 40, and we had to go down and cut it down, because some of them, even if it was very, very beneficial in energy usage, or it would mean a lot of gain in energy savings, but it would be not feasible with the current condition and the operation of the system, and also wouldn't be, even with changes in operation or the already available assets, wouldn't be feasible to maintain on the long run. So that's why these were the more scenarios we used, and as I mentioned, we also took into account what is actually feasible to do, and based on most of the important part and aspects was peak consumption, system demands, perspective, and energy consumption cost all together. But actually, there were many more KPIs that we took into account developing inside our model. So we altogether took into account the 10 scenarios that actually the colleagues and András will be present later on. This is I will explain in the next slides why and how we choose these. So actually, the scenarios take into account both technical and energy bias aspects of operations, and it's based on its energy audit is based on our hydraulic model that's calibrated for the already available data. Actually, we use the results as tabular report graphs for pump utilization. We calculated average power consumption and energy costs in different scenarios in time minutes time steps, which consider both energy and operation aspects. Also, we calculated peak, average, and minimum energy consumption, all of the pumps system-wise, and later on we were focusing on the pumps and pump stations. Actually, in our case, it was one big pump station that we had to mainly focus because that was taking some of most of the energy in our case. You can see on the right some of the outputs that's already available. This is actually some of the inputs and inputs for the analyses that REKK and András was making. And these are what's already available for the users as a tabular and graphical output for our cost analysis part and also the energy analysis part. As I mentioned, our main target in the end was the main pump station, Liman. As you can see it is on the other side, or on the other side of the Danube bank. As these main pump station was consuming most of the energy, and scenarios aiming the Liman pump station gave the best results for our further analyses. So actually, what we was taking about, it's we can summarize it in 3 main scenarios: either complete replacement, implementation of a bypass at auxiliary pump, or runtime or time modification of the pump. It's mainly these scenarios using the time slot or optimal energy cost was not always possible to fulfill the system demands or creating such hydraulic conditions that can cause operational problems. We were mainly looking for Enikő will show the energy sector forecast for the energy sector, and we were mainly using her findings about the energy sectors to aiming for that more optimal operation in aspect of energy consumption. So altogether, what we had is actually what we will be, as because of the time constraints, we cannot show all of our available scenarios. We will be using the Liman scenarios as main scenarios. As you can see, these are the main 3 elements what we were aiming for. So the complete replacement of the implemented pump with different kind of efficiency and larger performance reserve, or also like maintaining the current assets and adding auxiliary pumps or bypass pumps, we also making these changes, and also were making using the so maintaining the existing devices and implementation additional devices in order to reduce the load of the main pumps, to increase the efficiency and the reserve inside the pumps. So, and also we were making the different operational changes. So in what András will show, we will take into account the longer operational hours or different operational hours, and how does it affect the operation of all other pumps inside the network itself. So, and what we also use, these are the tools that actually we use for analysis. So both of graphs and tabular analyses are available. We use the MyPlus platform with water distribution extension, and also the WaterNet Advisor. This is the online tool for further analysis. It also contains some of these, most of our tools for this analysis as I mentioned, and these are what also will be implemented inside the water utility itself. And these were the tools that actually supplied the basis of the further analysis of András and other results.
So thank you, Erzsébet. And I would say as the last two sentences of that, I would say as the lesson learned for this exercise itself, which was really, I would say, a really complicated system, but very nice system, and took a relatively long time to arrive to this point, because indeed to find the best solution or the best options, it needs the iteration. It needs an iteration to understand the hydraulic, water quality, and energy relations by changing of the elements of the systems. And indeed, if we have the change of the daily price of the energy, if we take it into consideration, and we try to find the best solution, we always need to have a look whether the system capability allows that, as well as the hydraulic or the water quality conditions of the system, how would look like if we implement these measures. So as I would say, the summary of this work, when we go into this direction and making the changes and making all the measures implemented, it makes sense to apply a bit of more complex outlook, because there are potential bottlenecks of the systems if we are having a look only from one through one glasses, not necessarily we are able to see it. So it was really nice work, and let's say we are happy that we could contribute and we could calibrate the model and could hand it over the results in that form that water utility can use. So as Erzsébet mentioned, that this result is given into this WaterNet Advisor platform, which can serve as an internal sharing tool for the model itself, which is delivered, and to do the model analysis. So that was all what we wanted to say here. Indeed, there are many details of that, and it's quite interesting to speak about that later on. So I hope that you could enjoy the presentation. So thank you.
Thank you, Zsuzsa and Erzsi, for your presentation. Now it is the time for questions, if there are any questions. In the chat box, we have not received a question, but if anybody has something on her or his mind about the information so far heard, I think this is the time to ask. I have one question for Zlatko, but let me wait a few seconds before maybe somebody raises the hand or to speak up or sends a question through the chat. So Zlatko, the question that came to my mind, you were describing how there is no reliable data about the consumption up in the SRAM area, about the number of people, the inhabitants up in the SRAM area. And this is this will be useful information for you. But have you maybe tried to make an estimate based upon the consumption of the people, to estimate the number of people based on their consumption? If you hear us, yes, that's where you are.
Yeah, well, for the model, the most important thing about consumption is a database of consumers and consumption. We had a database from our company about consumption on the level, on the monthly consumption per house, per connection, per water meter, and it was quite correct database, which was georeferenced on the database layer, GIS layer. So each consumer was put just exactly where it is in reality, and that was easiest way to do. But for some other analysis, for example, for water losses, or for anything else that you want to be that is connected with the accurate number of population, in that sense we are not so sure in this projection of consumers, of population in this moment. This analysis, this model was related, I repeat, on the period of September 2018 to September 2019, because project started last year, but already now we see that maybe in the next year, in next period, we should update it. Of course, it's going to be updated immediately after a census of next year's census in Serbia.
Okay, thank you. Somebody was trying to raise a hand, I think, but then it disappeared. I don't see any raised hands now. Well,
there is a question though in the question session, sorry.
Oh, there's a question there. Information over time. Oh. The question is, how did you come to a consumption pattern for every part of the supply system if you don't know exactly the consumption? Or do you have consumption measurements for every part of the system? And how good could you match all the reservoir water levels with this uncertain information over time? There's a question. It's a complex question.
I think that's a question for me. It's tricky, actually. That was the most. That was the really the one of the most of the parts we spent on calibration, because we also calibrate not just you know, to measurements, but also to consumption and such. So it's actually a combination of two. As mentioned, Zlatko, there are several zones inside the network, and we could partially, some of the tanks have, so some of the zones could be developed easily, the consumption patterns for because it has gravity outflow, and each of the tanks are serving a smaller area that's connected to it for this smaller zone. So most of the smaller villages could be solved that way. The other part is actually developing based on these patterns, and also what Zlatko didn't mention, that they actually have a very detailed consumption reading information. So sometimes they have monthly readings for each of the consumers, sometimes even 2 or 3 weeks time periods. So that's why we knew exactly how changes. So we took the averages from the customer information system and connected with the patterns from the distances. So this is actually what also the IWA, the International Water Association, suggests were used, and this is where most of the cases were possible. Some cases were not enough, so that's why it's cannot be used all of the consumer data there. So that's where we have to make the assumption based on a zone again, and based on the zone consumption we distributed the consumption based on network sizes. There are different kind of possibilities of pipes, measure equal lengths of pipes. There are different options. We took into account the different measures, and it was part of the calibration process as well. I think it was enough. I can speak about it all day. The others know about it. We spoke about it in the workshop.
The other one is for Zlatko, I think, maybe more, because that's what I see. That's the quite interesting questions in terms of, you know, if you measure your system well, you can get much more better picture of your system. So that's for. The question is that how many pressure sensors are used in the network, and maybe that's also the question, the flow sensors, and are they battery operated pressure sensors in the network as well? So
I can tell the number, but the other question is for Zlatko actually, because I forgot. Altogether, it was for calibration itself, we used 20 pressure sensors, but there is more actually. We did not use all of it for calibration. We used some of for validation itself as well. And yeah, I think that, but it's more partially. The rest of the question is for. Sorry, I just take into my notes because it's the system. I always forget the system parts. So there are several, I would say, measurements on the system, which is very well designed. And I think it was the very good advantage of this one. But if Zlatko, I think this is Zlatko's let's use Zlatko's question.
Zlatko, would you like to add anything, or?
Could you repeat the question for me?
How many pressure sensors are used in the network? Are they battery operated pressure sensors in the network? So do you have battery operated or some other solutions that you deliver?
No battery supplied, but with the power. So permanent, an electric power connected source, flow meters and pressure meters also on the same points, especially and occasionally on inlets of settlement, so that they could be established as a DMA for the further non-revenue water analysis firstly. But not only for that, in this case, it was very useful tool and data for this modeling. And it was part of a project in 2002, so almost 20 years our water system has permanent SCADA online measurements of flows and pressures.
And we must say that these, I would say, locations and measurements are really well designed and well maintained, which is also very important. So as Zlatko mentioned, not just only the pressure meter, but also the flow meters are at place and the tanks, and these are at very good locations and very well designed locations.
Yeah.
Which is very important indeed if you would like to get out not just data but information from the system.
So that's for both of the questions. That's why actually these are interconnected, because most of the calibration process were possible because of the well-maintained and designed measurements. And they have a very long time series. That's also important. That you can learn a lot about the network, and we learn a lot about the network based on their own information.
Okay, there's one question, and I think this should be the last one before we move on. What type of communication is used? GPRS, LORA, I'm not sure what these are, and BIOT.
LoRaWAN.
LoRa. Okay.
So there's a question for, if Zlatko, you know, that LoRaWAN or other type of data transmission. Is there any preferred in your company, or?
As I know, it's a GPRS signal.
Okay, well, thank you very much. Since we get delayed, I suggest that we move on. And now Enikő is coming with her presentation on energy market price forecasts. Please, Enikő.
Thank you. I just try to share my screen. I hope you can see it.
We can see your PowerPoint, but not the projection yet.
Not yet. I tried to enter the full mode. Maybe. Okay, just a second. Maybe I just try to share the screen itself, and then maybe. Just a second. So.
We can see the presenter mode now. Presenter mode. Oh, now it's fine. Now it's good.
Okay, great. Sorry, I have two monitors, and sometimes. Okay. So thank you very much. As we are already ahead of time, I try to be as brief as I can, and then we will still have some more time in the question and answer session to clarify things. So what I would like to talk about now is the electricity price forecast that we carried out for this project, and also the logic of the energy cost calculation that was based on this forecast. So the structure of the presentation is that first I would like to share a few things about the market model itself that we use for this forecast. And then the main part of the presentation would be the exact electricity price forecast, and also the forecasted CO2 intensity of the electricity production. And then I will turn to the logic of the cost calculation. But actually all the results will be then summarized by András at a later presentation. What I would like to emphasize here is that the aim of this price forecast was twofold. As already mentioned, one target was to be able to quantify the actual cost savings. So when we know the electricity prices, then we can quantify how much money actually can we save with energy consumption reduction. But the other main focus was to see what are the different electricity price patterns in the future. So in that way, we can serve as an input for the final definition of the consumption pattern scenarios. Those will also be presented by András. And as it was already mentioned, this whole work was a very iterative one. So we have the hydraulic model, and then we have our modeling results, and then we shared all the results with each other and tried to come up with an optimized best solution, taking everything into account. So first, what I would like to show you is what is actually the price output of our model. I think it's important to clarify here that what we model is actually the wholesale electricity prices. And we have these prices for each hour and each country. So the model covers all Europe, not just the Serbian market. And once we have all this information, we can calculate different average prices. So monthly, yearly prices, but also the prices in the different periods of the day. So high and low periods or day and night periods, and also the average prices for a given hour of the day in every year. So this way we can see which periods of the day and of the year are the cheaper and the more expensive ones. So we can take all this into account when energy costs are optimized. And it is important that wholesale prices are of course not equal to retail or end user prices. So what we did here is that we used the wholesale prices as the basis of the estimation of the energy price component. So in our calculation, this energy component fee was a bit higher than the wholesale price itself, but actually that was the basis that we used. And just very few words about the model that we used. This is, as I said, a market model. This is an hourly based unit commitment and economic dispatch model that covers basically total Europe, so the whole electricity system of Europe, I would say. And this is very important because of the interconnectivity of whole Europe, basically, not just the region itself. So in this case, we could take into account the whole future expected developments in Europe regarding, for example, renewable penetration in different countries and their effects, all of their effects on the Serbian market at the end of the day. So the model does a weekly optimization to meet electricity demand in each and every country and also operating reserve requirements at the lowest possible cost. And all the hours of the year are modeled, and this way we can have a price forecast for them. And the main input parameters are the power plant portfolio. So both the fossil and the nuclear power plants are included on a unit level. We also have the aggregate capacities for renewables. So we are based our estimates on one hand on different national energy plans and strategies, and also on official EU forecasts regarding electricity mix in the future. And also we have interconnector capacities between countries, yearly electricity consumption, and different fuel prices. So what we see from all this, and I will turn to that in a minute in the different graphs, is that on one hand, from now on until 2040, we see increasing prices year by year. That is mainly driven by the increasing CO2 quota prices. And these also have effect in countries that now don't really, so in countries that don't apply ETS prices now because of the import and export possibilities. And also what we see is that there is a switch between the relative prices of the day and night periods. So now when we see the electricity prices the hourly electricity prices, we see that mostly the daytime prices are much higher than the nighttime prices because electricity demand is much higher in the daytime. What changes in the future is that with many photovoltaic panels, so with many solar energy in the system, the middle of the day, so somewhere between 8 o'clock and 18 o'clock, the electricity becomes much cheaper. And this is especially true in the summer months, so the price differences between winter and summer are also increasing in the future. So this is basically our forecast until 2045. Here you can see the average yearly prices. Baseload means the total yearly average, and then we had the different tariff periods, so night and day periods average for every year. And you can see this switch from around 2025, but very clearly there after 2030 that the night period tariffs are much higher than the day period tariffs. This is mainly driven by the solar energy. And this is also visible in this next figure, where we calculated for every year the average of every first, second, third hour of the day. And there you can see that if you have a look to this whole day, so from 1 to 24 hours, this effect of the solar generation is very significant after a point. And while at the beginning we have this shape where we have the higher prices in the middle of the day, then in the later future years, we have a very significantly lower period when the solar generation takes place. So this was absolutely something that was crucial to have a definition of a least cost consumption pattern solution for this project for the future years. And just a few words about the CO2 intensity of the electricity production. Well, the key issue here is that in the future, of course, we will have much less fossil production and much more renewable one. And this leads to drastically decreasing CO2 intensity of electricity production. Basically, from 2030, we have around 30 or even less kilogram per kilojoule CO2 intensity in case of the electricity production, while nowadays we are over 200, so this is absolutely a drastic decrease. And what we can also see is that, again, in the middle of the day, we have in the future this lower CO2 intensity because of the higher share of the renewable production in those hours. So this is absolutely in line with cost-saving efforts. So it's a good news that when we want to save cost, we will most probably save CO2 emission also. And just a very few thoughts on the logic of the cost calculation. So basically what we had as a starting point was the elements of the present pricing. So we received different existing bills from the partners, and based on that we created the future energy cost calculation. Most of the elements were kept at their present levels, but the energy fee was the one that changed across the years and the scenarios. And according to these bills, what we see now is that we have a high and a low tariff period. That is basically the day and the night hours of the given year. And the consumption is just put into these two periods, and we have these two different tariffs that are there, both for the network tariff elements and also for the energy component. And what we assumed in line with the liberalized energy market experiences, that later on the hourly tariffication will take place. That means that as we in the wholesale electricity market have different prices for the different hours, this can be also reflected actually in the bills, so at the consumer level. So if you have different consumption levels in the different hours, then you will also have different tariffs to be paid in these hours. So this is basically how the cost calculation look like. So we have the network fee element of the total cost that is in our assumptions for the future also equals to the existing structure. And then what is the main part where the restructuring of the consumption can have, and also the level of the consumption can have a great effect on the final costs, is the energy component part, where we have these hourly energy tariffs and also the hourly consumption from the hydraulic model. And of course, there are some other fees, such as some taxes and levies, energy efficiency levy, excise duty, and so on. And we took all this into account when we calculated the total cost. And then, of course, we can have these different scenarios with the different consumption patterns. So we will arrive to different energy costs in these cases, but this is something that András will tell you more about. So I just wanted to say all this, and I'm absolutely happy to have your questions after András' presentation. So thank you.
Yes. Thank you very much, Enikő. And let me share my screen for the last presentation, where I'm trying to pull all different threads together. Do you see my presentation now? The usual question.
Yes.
Good, thank you. So let's see how hydraulic modeling and energy market modeling and other elements come and provide the full picture. Erzsi was describing the wide range of scenarios that were analyzed, and out of these we selected the scenarios that make sense from the perspective of energy saving and water quality and hydraulics and so on and so on. And this resulted in a baseline scenario and 6 modifications of the baseline. What are the modifications? In S1, the original pump, which is Jugoturbina, this is the big pump that is supplying from the drinking water treatment plant, the SREM area. So this pump is exchanged to a brand new pump, and we were working with a specific pump just because we were able to get a cost estimate for that pump, KSB omega C. The same hours of operation essentially during the night and early morning. In case of S2, the original Jugoturbina pump is left, but there is a bypass pump, as it was explained by Erzsi, to reduce the capacity requirement to make it easier for the pump to operate. And this also requires a frequency control device. So this is a bypass pump and frequency modulator. Again, same 7 hours of operation. In S3, we still stick with the original pump. There is no bypass pump, but frequency control plays a role, because what we are doing is we are extending the hours of operation, again, to relieve the pressure on the pump. So instead of 7 hours, now it operates for 9 hours. And then the other 3 scenarios are essentially the same idea technologically, but the hours of operation shift out to the daytime hours, because electricity is expected to become cheaper during the day in a couple of years from today. So these are our basic scenarios. And here you can see how electricity consumption changes. The baseline is this blue area. It has a large consumption during the night and early morning. And then during the day, all the rest of the pumps together make up relatively modest consumption. This is the consumption of the whole SREM area. Much of the consumption is related to the so-called Liman pumping station, the role of which is to pump the water up to the reservoir on the hill. But also distribution on the hill requires electricity, so that's why there is a fairly constant electricity use for most of the day, except for the hours when the big pump is used to fill the storage area uphill. Here you can see this 468 kilowatt. That's the average daily capacity utilization of the scenario. If the pump is changed to a modern pump, then you suddenly see a big drop during this peak operation, and then the same daily operation. With the frequency modulator, the change is not so big, but still quite substantial compared to the baseline. And in case the hours of operation extend from 7 to 9, then we'll have lower consumption during the peak hours and continued operation for 2 more hours before coming down to the usual segment. So these are the baseline scenario and S1, 2, 3. Here, same story, same technological applications, except that now the hours of operation in the scenarios shift from the night to the daytime because of the expected price drop during the day, due mostly to the solar penetration, large solar volumes. So very similar, but we still had to model it because there are different consumption patterns during the day and during the night, and it's important for us because whatever happens on the system, as it was explained by Zsuzsa, it has an impact on something else. So we cannot just simply assume that we have the same consumption as in the night. During the day, it is somewhat different. Not much, but there's a difference. From the original 7 scenarios, we created some combinations. So we have the baseline, and then there is this pump change scenario. But we assumed that from 2025, we are shifting the hours of operation. Same technology, but the new hours of operation, because from that point on, it becomes more attractive. With the bypass and frequency modulator, same story, but the shift already happens earlier. And with the frequency modulator and 9 hours of operation, the shift happens already in 2022, mostly because the 9 hours of operation already extend into the morning rush hours as far as the morning peak consumption on the network, and this is creating a slightly different consumption profile, and it makes sense to already shift the consumption to the daytime hours. So it can happen actually rather soon on the open liberalized electricity market. We also did a shift in the baseline because as we inspected the scenario, it turns out that from 2025 it makes sense to shift from the night to the daytime hours. So we have 4 scenario combinations, and these are the ones that we are going to compare. We also had some hydraulic model runs in which the hours of operation were split. So some of the peak hours stayed in the night, some of the peak hours went to the daytime regime, but running these pumps at peak capacity twice a day means some problem for the network hydraulics. It can create pressure fluctuations, and that can result in breaking pipelines. So we eventually disposed those scenarios, and we stick with the ones that you see on the screen. So we did the cost-benefit analysis. What are the main components? We are looking at the current investment costs, changes in maintenance costs, future electricity cost savings. We are also looking at the carbon emission savings, but we didn't make them part of the CBA, the cost-benefit analysis, because that's like one large step how to sell carbon savings. So we will cover that, but we didn't make it part of the balance, CBA balance. And we calculated present value for all scenarios and also internal rate of return. For present value calculations, since we are running short of time, I don't want to spend now time on this, but if you have been doing cost benefit analysis, you know that any money that's further out in the future, it means less current value for that money. Same as with a bank account. If you put some money into your bank account and there is an interest rate, then in the future that money will be more valuable. It will have earned some interest rate. With discounting, we do the opposite. We are looking at the future value and calculating the current lower value. So this is what we have been doing for all the scenarios. And let's see what are our main assumptions. For the baseline, there is no new investment, but there is an expected reconstruction cost that will take place sometime in the not very far future. And we estimate the cost of 50,000 euros. We also have a maintenance cost for the pump, the Yugo-turbina pump, estimated at 6,000 euro per year. And these are the investment costs for the scenarios with a pump change, bypass pump, and frequency modulation, or only frequency modulation. So you can see this is how much would need to be spent right away. But in exchange, there is a lower maintenance cost annually, and also there are lower electricity costs, as already suggested by lower electricity consumption figures. We also did a stress test of our scenarios, just assuming that the situation is not as rosy as it originally looked. So what if the reconstruction cost is actually not 50,000 euros but less, so making the baseline more attractive? Again, what if maintenance cost is lower, making the baseline more attractive? And what if the investment cost of all these different technologies are more expensive, so making these less attractive? So we are also trying these figures to see if assuming less attractive components for our cost-benefit analysis would still result in an attractive or wouldn't result in an attractive outcome. This is the diagram about the annual energy costs of the SRAM area in euro. You can see that it's about 200,000 and 220,000 euros today, but because of the rising electricity prices, it will increase to about 300,000. However, installing new technologies will save substantial amounts of the electricity bill. These are the savings, so the comparison to the baseline. In case the Yugo-turbina pump is replaced with the modern pump, the savings could be up to 25,000 euros per year. With the other technologies, there are still substantial savings, 10 to 20,000 euros per year. Okay, and here we have the discounted values of all the savings, electricity cost savings in 25 years. If we have just the nominal values, which means we're applying a 0% discount rate, then we have these figures, 380 to 550,000 euros altogether in present values, covering the 25 years. But even if we apply a discount rate, the larger the discount rate, the less valuable some future saving is for us today. So if we apply a discount rate, then that will reduce the present value of the savings, but still these are substantial figures, 200,000, 300,000, 400,000 euros, depending on which investment, which measure we pursue, and depending on the interest rate. So putting all the pieces together, comparing to the baseline, these are our figures. Concerning the investment cost, in the baseline there would be some reconstruction cost, but compared to the baseline, there is no shift. Buying the new pump would still result in cost. Cost items are with negative sign. However, these other two technologies would be less expensive in present value terms than the baseline reconstruction cost. So actually there are already some savings. And then if you look at maintenance costs, there are continued additional savings. The electricity costs, again, there are savings. And here we assume the 1% discount rate or interest rate. So altogether, the value of these scenarios is between 400 and 550,000 euros for the Novi Sad Water Utility company. If we do the stress test, as I mentioned, we are putting more rigorous assumptions. We are not as optimistic about the components of our CBA. Then we still have 300 to 400,000 euros of net present savings because of these investments. So these are quite good. Same story if we apply a 3% interest rate. We looked at financing opportunities and we concluded that 3% is probably the highest end of possible financing costs. So we shouldn't even consider higher than 3% because either state financed loans or some preferential loans from other sources can be attained at this interest rate or below. So same story, we have attractive investments even under the stress test scenario. So this is, I think, quite good, quite attractive. And if we look at the internal rate of return, that's it is looking at the equivalent of like doing an investment. So you are doing an investment like a pump change, and how much return it would generate annually. And here we see a figure of 49%, which is extremely good. That's very, very good. If you go to a bank, you may get 1% for your money. If you invest in the pump change, it's like investing money at a 49% interest rate. Of course, you cannot do it every year buying new pumps because it makes sense only once, but it has a very good investment profile, which means that there's a payback time of only 3.5 years. Again, something very attractive. With the other two investments, the figures are even better, but that's only because you are putting in smaller money. The original investment cost is lower. And with this lower money, you are still generating lots of energy savings. So very good return periods, just 2-3 years, and the original investment is already repaid. And then for the remaining time of the investment, for the additional 20-22 years, it keeps generating energy cost savings. That's why these figures are so good. If there are some less optimistic assumptions, we are still talking about good rates of return and payback time of maximum 6-7 years, which is, I think, still quite attractive. Now, what about the carbon emissions, which was already mentioned by Enikő? These are the total carbon emissions behind the current electricity consumption. And as it was indicated by Enikő, the carbon intensity will drop. But if we do the investment today, we are already saving some carbon emissions because of the lower electricity consumption. These are just the differences between the different scenarios. So a couple of 100 tons of CO2 per year can be saved for the next 5 years, and then it will keep declining. So altogether, compared to the baseline, more than 2 kilotons of carbon emissions can be saved. And if we look at the European emission trading market, which has a quite transparent price, we can, based upon that, we can assume that the value of a ton of CO2 emission reduction is about 50 euros. And with this 50 euros, the total benefit from a CO2 reduction is more than 100,000 euros. Now, if you recall the figures, I told you that the investment cost would be generally less than 100,000 euros for any of the scenarios. And even the carbon emission savings, the value of these savings is higher. So this shows that these investments are good not only strictly from a financial perspective, and they are excellent investments from a financial perspective, but they are also good from the perspective of quantified emission reductions, from the perspective of the value that is placed on emission reductions in the market. So this is my presentation. Thank you very much. And I'm quitting from here, from the presentation, if I can. I think I have already done that, or Kati did it for me. And even though we are at the end of our session, I would like to ask if there are, yeah, I see some questions here. What is the actual, I'm sorry, can I just close the window because it's the bells are ringing outside. Yes, what is the actual percentage of energy cost compared to the total operation costs of Novi Sad utility? And what are the projections of the project to reduce the energy costs? The projections, energy cost reduction, I have shown it to you. In present value terms, it can be a few €100,000 for the percentage compared to the total operating cost. Maybe Daniela, if you hear me, maybe can you answer that? Total energy cost compared to the total operating cost. I don't have it from my heart. We don't see it, but from other water utility companies. Oh yes, Daniela is here. Good.
Sorry, András. Could you repeat the question? I didn't hear.
Yes, the question was, what is the percentage of the energy costs compared to the total operating costs?
Well, we didn't do that kind of analysis.
Okay.
We sure have to do that in the future.
Okay.
Okay.
But let me just say that in other companies in Hungary, we have seen figures ranging from 15% to 30% usually for energy costs. Of course, it depends on the market. If you receive energy at a regulated price, at a market price, and how efficient your system is, whether it's a hilly system or it's a flat area, whether you have deep underground sources or not. So there are some factors that can really increase the share of your energy costs to 30, even higher than 30%. And then there are some factors which keep it down around 10-15%. I'm just looking at the questions, if there's any other question. Okay, somebody said that didn't see the bottom of the slide, but we will also post the slides on our website, so you will be able to check it out in its full extent. So I would like to ask if there is any other question on anybody's mind, because if not, then I think we had a rather compact 2 hours behind us. Lots of information, lots of things to digest. I think bottom line is that pulling together different professions, having a very well prepared water utility with lots of data, a good GIS database, having hydraulic engineers with excellent tools and preparation, and adding a touch of economics. I think it can uncover opportunities which are otherwise not necessarily apparent, not necessarily clear to us. At least that's my conclusion from this project. And as I said, we will post both the slides and also the presentations to our website, which is rekk.hu. So it will happen soon. And if you have any questions about this session in the future, please contact us or contact our colleagues in Novi Sad or at DHI Hungary. And with this, I would like to close the webinar, unless anybody has any other statement or conclusion to add. Okay, thank you very much for your attention. I hope this was useful, and again, let me encourage everybody to come back to us with questions or comments. We are eager to hear your feedback. Thank you very much again, and enjoy the rest of your day.
Thank you.
Bye-bye.
Thank you.
Thank you. Bye.
Bye.
Bye-bye.
Mhm.